Hello everyone. Today I will discuss the solution of RMO 2019 problem 6. So here is the problem statement. Suppose 91 distinct positive integers greater than 1 are given such that there are at least 456 pairs among them which are relatively prime. Show that one can find 4 integers a, b, c, d among them such that GCD of a, b is 1, GCD of b, c is also 1, and GCD of c, d is also 1, and GCD of d, is also 1. So seeing the problem statement, we see that the GCD appears pretty unexpectedly. So we suspect that GCD might not be such a relevant factor to solving the problem. What I mean is, it is not a bad idea to remove GCD. As in, suppose 91, so we rephrase the problem statement. Suppose 91 distinct positive integers greater than 1 are given, such that there are at least 456 pairs of them which satisfy some condition. In this case, we have relatively prime, but we try to remove GCD. So we say this satisfies some condition. Show that one can find 4 integers a, b, c, d among them, such that a, b satisfy that condition, b, c satisfy that condition, c, d satisfy that condition, and d, e also satisfies that condition. So at this point, what we are basically doing is we are making a graph G. So you're making a graph G with 91 vertices and 91 vertices corresponding to the 91 positive integers we are given. And an edge between two vertices a, b. We have an edge between two vertices a, b if and only if GCD of a, b is equal to 1. Great. So we are constructing this graph, and what we know is that there are at least 456 edges in this graph. And what we want to find is 4 integers a, b, c, d. 4 integers a, b, c, and d. Oops. Such that GCD of a, b is 1. That is, there is an edge between a and b. GCD of b, c is 1. Sorry, I'll just read this. GCD of a, b is 1. And GCD of c, d, b, c is 1. Because b, c have GCD. I'll repeat this part. So what we want is 4 integers a, b, c, d, such that GCD a, b is 1. So there's an edge between a, b. And GCD b, c is 1. So there's an edge between b, c. GCD c, d is 1. So there must be an edge between c and d. And GCD d, is also 1. So there is also an edge between a, d. So what we want is a cycle of length 4. Cycle of length 4. Or in short, a 4 cycle. So we have a graph G on 91 vertices with at least 456 edges, and we want a cycle of length 4. Now, first of all, 91 and 456 might seem random numbers, but note that they're not that random. 456 is equal to 91 times 5 plus 1. So there's a nice relation of 456 in terms of 91, which is nice. And generally 91 is like any number that they've most likely chosen. So it might not be a bad idea to say 91 is equal to n. And 456 is equal to 5n plus 1. So rephrasing our problem, we have a graph G on n vertices with greater than 5n edges, or greater than 5n edges, and we want a 4 cycle. So assume, for the sake of contradiction, assume G has no 4 cycle. Assume G has no 4 cycle. Now we employ a standard idea for such kind of problems. We try to count a certain structure. What do I mean by this? Is in this case, we try to count the number of two length paths. So we count number of two length paths. So what is the two length path? Is three vertices u, v, w, such that u to w is connected. There's an edge between u and w, and there's an edge between v and w. So in this case, we are counting the two length paths, so that there is an edge between u to v and an edge between v to w. Let x be the number of such two length paths. Now, why are we counting two length paths? So first of all, what we will try to do is we will count this structure in two different ways. So now why are we counting two length paths? Because if we fix u and w, so we fix u and w and find the number of v such that u to v is an edge and v to w is an edge. And note that at most one such v exists. Now, why is this true? Because say if there were another v, say u is connected to v, which is connected to w, and u is also connected to some vertex v prime, which is also connected to w. But in this case, we now have a fourth cycle. And we assume that graph G does not have a fourth cycle. So we must have at most one such v. Great. So number of two length paths which we labeled x must be at most the number of pairs of vertices u, w. Now that u, w must be distinct. So this is at most n choose 2, as we had n vertices. Now we try to count x in a different way. We count x by fixing v. Last time we fixed u and w, now we fix v. Now for fixing v, we want to count number of u, w such that they are both connected to v. Now the set of vertices connected to v, now the number of vertices connected to v is the degree of v. Call it dv. dv is degree of v. And the number of distinct vertices u, w is dv choose 2. So this time we have x is precisely equal to summation dv choose 2 for all vertices v, where we are summing this for all vertex v. So we have the following inequality. Summation vertex v, we're summing this for all vertices v, where dv is the degree of v, we are summing dv choose 2 for all vertices v, and this must be less than equal to n choose 2. Great. Now, what do we know about degree? We know that summation dv is equal to twice the number of edges. I will write just summation without the limits because for convenience, all summations would be summing for all vertex v. So we have that summation dv is twice the number of edges. So let us try to rewrite this inequality into something better. If n choose 2 is greater than equal to summation dv choose 2, which is equal to summation dv squared by 2 minus summation dv by 2. Where we use that dv choose 2 is dv times dv minus 1 divided by 2. Now this quantity is equal to summation dv squared half of summation dv squared minus e. Great. Now, how do we relate summation dv squared to summation dv through an inequality? The answer is Cauchy-Schwarz. So by Cauchy-Schwarz, we have that this is greater than equal to half of summation di whole squared divided by n minus e. This is equal to half of 2e whole squared divided by n minus e, which is equal to 2e squared divided by n minus e. Great. So we have the following simplified inequality. N choose 2 is greater than equal to 2e squared divided by n minus e. Now what do we know about e? Recall that we had e is strictly greater than 5n. So let us try to use this here. Now we can write this thing as E times 2E minus N divided by N. Now note that E is greater than 5N. And 2E is greater than 10N. So 2E minus N is equal to 9N. Sorry, is greater than 9N. So both of these quantities are positive, so we can multiply them. So we have that E times 2E minus N is greater than 45N squared. Dividing by N, which is also positive, we get that this is equal to 45. Oops. 45N. Great. So we have the following inequality. N choose 2 is greater than 45N. But recall, we said N is equal to 91. So this means 91 choose 2 must be greater than 45 times 91. But what is 91 choose 2? 91 choose 2 is 91 times 90 divided by 2, which is precisely equal to 91 times 45. So if our assumption was true that G has no force cycle, then we must have that 91 times 45 is greater than 91 times 45, which is obviously a contradiction. Hence, the first assumption, that is G has no force cycle, must be true. Hence, G has the force cycle and we are done. So this is the graph theoretic solution to this problem, which I found more natural. I hope you like it. I will also explain the official solution to this problem. So the official solution constructs a grid of 91 plus 91 grid. So we have a 91 plus 91 grid. We have 91 rows and 91 columns. And let A1, A2 to A91 be the numbers. Now we color a cell in a particular, a cell black in a following way. Say the cell is in row I and column J. Then we color the cell at row I, column J at row I and column J. Black, if and only if J is equal to 1. So how many black cells would we have this time? Note that a particular GCD of A comma B is 1, blackens 2 cells. One at row A and column B, and the other at row B, row B and column A. Column A. So in our grid, we have at least 950 or I'll write it as 46. 456 times 2 cells black. Again, we will use that 456 is equal to 91 times 5 plus 1. So we have at least 91 times 10 plus 2 cells black. Great. So what do we want? We want 4 numbers A, B, C, D. Is that GCD of A comma B is 1, GCD of B comma C is 1, GCD of C comma D is 1, and GCD of D comma A is 1. So what does that mean? GCD of A comma B is 1 means the number at row A and column B is black. row A and column B. This cell is black. Now we have that GCD of B comma C is also 1. This implies that GCD of C comma B is also 1. If C comma B is also 1. So the cell at row C and column B is also black. So this cell is also black. And we also have that GCD of C comma D is 1. Hence the cell at row C and column D is also black. And GCD of A comma D is also 1. So the cell at row A and column D is also black. So if we can find some structure like this, which looks like a rectangle, because they are in the same, like these cells are in the same row and these cells are in the same column and same as these and these. So this looks like a rectangle with vertices black. So call such a thing a black rectangle. Black rectangle. So if we can find a black rectangle, we are certain to find the condition that we want. That is, we can prove the problem. So in a grid with at least 91 times 10 plus 2 black cells, a 91 plus 91 grid, with at least 91 times 10 plus 2 black cells, we want a black rectangle. So let us try to find this. So this time also we count something. We count number of pairs of black cells in a particular, in a column. In cells in a column. That is, for any column I, we count the number of pairs of black cells in I. Here some cells, say these 4 cells are black. Then we count all such pairs. That is, these 4 choose 2, which is 6 pairs. So now let S denote the set of all such pairs. Set of all such pairs. So let us count S. So let Ci be number of black cells in column I. So the number of pairs of black cells must be Ci choose 2. So the number of elements in S must be precisely summation Ci choose 2 for I going from 1 to 91. Great. Now note that each element of S belongs to 2 different pairs of columns. So each element of S, each element in S, each element in S. So say we have an element in S, 2 black cells. For example, these 2 black cells. Now these belong to 2 different rows, right? Like these 2 black cells say belong to the 3rd row and the 7th. So each pair of black cells, that is each element in S, belongs to 2 different rows. And we have exactly 91 choose 2 rows. So if number of elements in S is greater than 91 choose 2, then by pigeonhole principle, 2 elements in S must correspond to the same set of pairs of rows. I will repeat this. Now consider for each element in S the pairs of rows that element is in. For example, we consider this black cell and this black cell. This is a pair in S. So these 2 belong to 2 cells. These 2 cells belongs to 2 different rows. Say they belong to the 3rd row and the 7th row. So now consider each such pair for each element in S. As there are exactly 91 choose 2 pairs of rows, by pigeonhole principle, if the number of elements in S is greater than 91 choose 2, 2 elements of S must correspond to the same pair of row. So let's see what happens if this is true. That is, we have two elements of S which correspond to the same pair of. Now, for convenience, say that this pair of rows is 5 and 11. So we have this 5th row and we have an 11th row, and say a column I. And an element in S must be a pair of black cells, and we are assuming that it is in column row 5 and row 11. Then we know that, so we are assuming that there is another cell, that is another element in S, which also corresponds to the row 5 and 11. Let that element be in column J. Now, any element in S is a pair of black cells, and those black cells must belong to row 5 and row 11. This means in column J, this cell must be black, and so must this cell be black. But so we exactly get a black rectangle, which is exactly what we want. So if the number of elements in S is greater than 91, choose 2, we are done. So all we need to do is check this. So let us check this. We have that summation Ci choose 2 for I equal to 1 to 91 to be greater than 91 choose 2. We want this. Now, what do we know about Ci's? We know that summation Ci is the total number of black cells in the grid, which we showed is greater than equal to 91 times 10 plus 2. Now, this plus 2 is just an annoying factor, and we can just say that this is greater than 91 times 10. And if our bound turns out to be weak, we can later redo all our bounds with the plus 2 factor. Now we will try to do a similar method as we did above. Summation Ci choose 2 is equal to summation Ci squared by 2 minus summation Ci. Let summation Ci denote M as the total number of cells in the grid. So this is equal to half of summation Ci squared minus M. Now again by Cauchy-Schwarz, we have that this is greater than equal to half of summation Ci whole squared divided by 91 minus M, which is equal to half of M squared. Oops, I missed the divided by 2 factor. This is divided by 2, this is divided by 2, this is divided by 2. Half of M squared times 91 minus M by 2. Hence we have summation Ci choose 2 is greater than equal to M squared minus 91M divided by 2 times 91. Now, if we can show that this, if this is greater than 91 choose 2, we would be done. So note that M is greater than 91 times 10. M minus 91 is greater than 91 times 9. As both of them are positive, we can again multiply these. So M square minus 91M is greater than 91 times 10 times 91 times 9. Now 2 times 91 is positive, so we can safely divide. 2 times 91, cancelling out a factor of 91, cancelling out a factor of 2. We have that this is equal to 91 times 45. Now what is 91 choose 2? 91 choose 2 is 91 times 90 divided by 2, which is also equal to 91 times 45. And we just proved that M square minus 91M divided by 2 times 91 is greater than 91 times 45, which is equal to 91 choose 2. Hence we proved what we wanted, and we are done. I hope you liked both of the solutions. Thank you.